Hello everyone, my name is Adam and this is our presentation. So my teammates are made of Khairina, Rubendran, Miza and as well as Ahnaf. But unfortunately Ahnaf couldn't make it because of internet problem. Without further ado, let's move on. Hydrogen is one of the leading alternatives for renewable energy resources to meet the high demand of energy from across the globe. So moreover, it actually is one of the highest demands in the chemical industry, 90% of which comes from the fossil fuel derivatives such as methane, methanol, ammonia, and such on. So it has also many other various applications. So as you can see in the slide, such as storage, gas grids, as well as the electricity system.
Steam methane reforming, also known as SMR, is a catalytic process that involves a reaction between hydrocarbons such as methane and steam. The result is a mixture of hydrogen, carbon monoxide, and carbon dioxide, and water that is produced in a series of three reactions. Methane reacting with steam at 700 to 800 degrees Celsius. SMR process is an endothermic process and requires additional heat to proceed. Therefore, furnace is introduced to provide heat to the reformer. Reformer reactor accomplishes most of the methane reforming. As for the water-gas shift reaction, this process is utilized to increase the hydrogen content, and the reformer products are fed to a WGS reactor where the equation CO plus water to produce CO2 plus hydrogen. The WGS is an exothermic reaction in nature. The WGS reactor is modeled as a single-stage reactor and operates at constant temperature and pressure. The temperature will increase in the reactor due to the exothermic nature of the shift reaction. Le Chatelier principle. Once the concentration of reactant, which is water, increase, the reaction is more favorable to react forward, which is producing product carbon dioxide and hydrogen gas. For the type of reactor,
packed bed reactor is used as a reformer for both process SMR and WGS. This is because
PBR is equipped with a catalyst bed, and since SMR is a catalytic process, so PBR is chosen to make sure that the reaction that occur within the reactor is efficient.
and PBR are tubular and filled with solid catalyst particles inside, and most often used to catalyze gas reactions. And the chemical reaction takes place on the surface of the catalyst.
Catalyst chosen is nickel catalyst because it has high reactivity, low attrition during test collection, and can resist a very high temperature. It is suitable to be used for SMR reaction because SMR operates at high temperature between 700 to 1200 degrees Celsius.
How packed bed reactor works for the hydrogen production. Typical bed reactor consists of a chamber such as a tube or a channel that contains
Catalyst. The liquid interacts with the catalyst across the length of the tube, altering the chemical composition of the substance. As for example, here for SMR, the reactant is methane and steam. The methane and steam will enter the tube and will pass through this bed of catalyst, and this catalyst that we chosen is nickel, and this nickel will alter the composition of the reactants to produce our desired products, which is carbon monoxide and hydrogen.
The chemical reaction takes place on the surface of the catalyst, and the conversion is based on the amount of solid catalyst rather than the volume of the reactor. Therefore, it is important to determine the right amount of solid catalyst needed. Tubular packed bed reactor with small diameter have the advantage of providing highest surface to volume ratio. This results in decreasing mass transport and heat transport resistance, make them attractive for achieving efficient thermal and mass transfer rates. Turbulent reactor is preferred because we need that turbulence to ensure a perfectly mixed flow, to ensure that we are getting high conversion of the reactants to produce higher yield of our desired products. There are few important factors that we need to take into consideration when designing this reactor. First is the heat transfer. Good heat transfer allows for longer tube life and increased reaction. Second is pressure drop. A low pressure drop allows for more methane to be processed.
So the overall block this is the overall block diagram for the steam methane reforming plant. Okay, first, the methane react with steam to produce synthesis gas including CO, CO2, and water. Then the synthesis gas is injected into the water shift reaction unit. The CO reacts with water in this unit to produce more hydrogen. And next is the process is continued by injecting the product into the CO2 removal unit, where absorption system separates CO2 from our product. And finally, to achieve higher purity of hydrogen, the product is fed into a methanation process through the
There are 6 reactions that occur simultaneously during this SMR and WGS process, but we are only focusing on these 3. There are 2 desired reactions and 1 undesired. Okay, based on this selectivity equation that we have evaluated is
we need to increase the concentration of A and B, which is methane and water, and we have to lower the concentration of CO. This is because according to this equation, concentration of A and B is directly proportional to the selectivity. So in order to increase the selectivity, we need to increase the concentration of A and B, and as for C, which is carbon monoxide, it is inversely proportional to the selectivity. So therefore, we need to lower the concentration of CO to make sure that selectivity is high. Second is semi-batch reactor by a membrane reactor of PFR with side streams and series of small CSTR.
For the reactor sizing, we can use this formula to calculate the weight of the catalyst, since the conversion of reactant depends on the weight of the catalyst rather than the volume. We can use the density formula to calculate the mass of the catalyst, and then using the ratio of 3 of length to diameter, we can get the 140 for diameter and the length of 4 to 1 meter. And WGS, we can use the same technique to calculate the mass of the catalyst.
So moving forward to our next column is going to be the carbon dioxide removal unit. So this particular unit is going to follow the application of an absorption column. So because it's an absorption column, so there's going to be 2 input flow and also 2 output flows. So in a typical absorption column, it's actually the gas from one of the input flows is going to be absorbed by one of the input liquid flows. Alright. Basically, if you look at this diagram, this is actually our schematic diagram for this particular system, where as I said earlier, the gas is going to be absorbed by the liquid. So basically in this situation, the gas is going to be carbon dioxide gas, and the liquid solvent, after having a thorough research, we have came to a conclusion that we're going to pick tetraethylene pentamine, or short form is TEPA, as our liquid solvent. Okay, so now the question is, why did we pick TEPA as our liquid solvent? Okay, so basically there are 2 reasons. If you can see closely, these are the 2 graphs which shows and which signifies why TEPA is actually a very good solvent to absorb carbon dioxide. First of all, the first graph, it shows that TEPA has the highest absorption rate of amines against the amount of carbon dioxide. And this graph actually shows a comparison of TEPA with so many other types of amines, and it shows that TEPA has the highest, so that's why we picked TEPA. But it's not just that. If you refer to the other graph below, it shows that TEPA also have the highest absorption rate versus loading curves. So because of these 2 reasons, we believe that TEPA is a good liquid solvent to absorb our carbon dioxide in our carbon dioxide removal unit. Okay, so after picking our liquid solvents, we have to make our assumptions so that we can ease our calculations later on. So I'm just going to highlight a few important assumptions. One of them are other components in the systems are not going to be affected by the absorption process, meaning that this particular CO2 removal unit is just going to affect the amount of carbon dioxide and also the TEPA. So it's like the amount of carbon dioxide is going to be larger than the amount of carbon dioxide exiting, hence carbon dioxide removal. Okay, so also another assumption is that the amount of TEPA entering the column is going to be equal to that exiting. So it's going to make it easier for us to calculate at the end of the day. And also we have to make sure that we define the system boundary as only to the part of the column so that nothing else like surrounding it is going to interfere with our calculation. Yes, so the other are also as important, but I'm not going to highlight in this presentation. Okay, so this is the modeling equations that are to be used in calculation. So basically the first and the second one is to calculate the fractional composition, where as we all know the total of x and the total of y is supposed to be 1, and then there's also the value of flow rate, where entering flow rate have to equal to exiting flow rate. And also because it's a carbon dioxide removal unit, we also have to know the amount of carbon dioxide. So the amount of carbon dioxide entering is also equal to the amount of carbon dioxide exiting the carbon dioxide removal unit. Okay, so once we are done with all these calculations, we have to conclude on our efficiency of our carbon dioxide removal unit. So because of that, we have to count the percentage removal of carbon dioxide, which from this particular situation, after calculating, our percentage of removal is 58.3%, and that is quite high for the removal of carbon dioxide. That's all.
The upcoming slide shows about the selection of absorbent, which is activated carbon and zeolite. It is essential to determine the types of absorbent used as it affects the overall rate of absorption and overall plant efficiency. The activated carbon has a greater surface area and microporous ability. There are few reasons why activated carbon is a very good absorbent. It involves the right and precise regulation of regeneration cycles. The absorption capacity for activated carbon is the highest for CO2, followed by CH4, CO, N2, and finally H2. This suggests that its selectivity towards CO2 is very high, meanwhile its selectivity to H2 is very low. Thus, the activated carbon will only absorb a very minuscule amount of hydrogen in its loading capacity. For the next absorbent, which is zeolite, zeolite is also a very good absorbent. It's aluminic silicate solids that carries a negatively charged particles, a structure of micropores which only absorb environmental neutralization of molecules. The absorption capacity for zeolite is the highest for CO2, followed by CO, CH4, N2, and H2. This shows that in the second layer, all the CO and CH4 will be absorbed. Not to mention that selectivity of H2 is also low in the second layer. This shows the zeolite is small with smaller capacity and a greater negative charge, have more H plus absorption ion.
As you can see, we gathered some information from the article. So this will tell us what's the absorption column going to be like. So for the cycle configuration, we decided that we would go for the 4 bed line steps. So we think that this is the most favorable as it has the highest purity and the highest recovery rate. So next, this is just to visualize what's the absorption column going to be like. Let's talk about the overall mass balance. So the composition of the component that as the feed to the absorption column. So we are given with the mass flow rate, so we just convert that into molar flow rate and need to find the density before converting that into to volumetric flow rate. So from the volumetric flow rate, we know the compositions for the feed as well as the outlet of this absorption column. So from here on, we can find the mass balance. So we can find what's the total volumetric flow rate that is going out. As highlighted in the red lines, they are the mass transfer zone. So this indicates that it's the unused bed. So we can know that what's the height of bed, which is 5 meters. So for upscaling, we just use the formula. So HB new. So we can get it's 5.44 meters. Then from here, we just use the ratio of HB new over HB equals to TB new over TB. So we can know what's the TB new now, which is
652.63 seconds. There are 6 strategies. So first of all, we need to use the process modeling and simulation software, because they can actually deliver faster and much more accurate results and predictions of these expected calculations. Next, we can actually increase the PSA columns. So if we have more, it is shown that nowadays there are available designs up to 12 beds with 8 steps, in which they can actually achieve better results with less impurity. So then we can also increase the mass transfer zone, which by scaling up the bed length and internal diameter of the column, it's actually directly proportional. So thus the MTZ will also increase. When we reduce this time, it actually results in higher kinetic limitations and resulting in increasing mass transfer zone. So increasing mass transfer zone will actually increase. So next, the 5th one is actually having an efficient regeneration and recovery rate. Lastly is the suitable operating conditions. So for adsorption, it actually requires high operating pressures with low temperatures. However, with desorption, it's an endothermic process, so it needs high temperature with low pressures. So in this presentation, we have talked about every single unit process, which has SMR, WGS, CO2 removal, as well as H2 enrichment unit, which is the adsorption part. In the future, we can actually use this. We would use this for better predictions and calculations. So we can compare our manual calculations to the simulated ones. Also use now machine learning, so they can use decision trees as well as artificial neural network. So lastly, we will talk about the reflections with our group project. So our submission was quite last minute, and we thought that because we were just shy and not confident enough to speak up or encourage each other to start working better and faster. So in terms of how we evaluate that, is that why does this happen is because we don't have enough teamwork due to the lack of communication and common understanding. If we go back to the root, it actually goes back to the communication, because communication is key. When we don't have that, we cannot really work together. So as a measure, next time in the future, we would actually have a more fixed time management, and maybe we can have more transparency in terms of how our work, as well as collaboratively flexible with each other. So our action plan is that we will actually develop a timeline for tasks and individual delegations, so we can stick to them, be more strict to them.